Greetings and welcome once again to my new calculus channel. So somebody here posted a comment. I don't know who this person is. And the comment says, it seems you have derived an expression for the locus of parallel secant lines for a function parameterized by pairs that make your auxiliary equation equal to zero. That's absolute rubbish. And I don't know whether this guy is trolling me or not, but let's give him the benefit of the doubt. That's total garbage. And I answer that here. I say, no, that is incorrect. Q of xmn, as you see over here, this expression, okay, is the slope difference between the tangent line and the parallel secant line. Hence, it must be zero. It is zero. It never is anything else but zero. And that's elementary geometry, by the way, okay? Has been known over 2,400 years ago. So he says, but in practice, it would be difficult to find those pairs for more complicated functions without a computer and numerical methods. That's absolute rubbish. It's not true. All of these can be found. Some require more ingenuity than others, but every single one of them can be found. Now, if he had bothered to read, or she had bothered to read the new calculus, single variable, he would have seen that all this is explained in chapter 11, which is the new calculus derivative definition. And it tells you that the whole expression containing m or n, and it doesn't matter if x is in one of those expressions, that expression will always be zero. So one can always find the derivative without even knowing x, mn, because the derivative is the expression with no terms that contain m or n, okay? So it's very easy to find the derivative. You don't really need this expression. It's just a powerful feature that accompanies ingenious or brilliant methodology and systems, okay? And it basically shows how when you think systematically and validly, you gain a lot of extra things, unlike your bullshit mainstream calculus. So some of the objections that have been raised, it says, how do you know if a parallel secant line to any given tangent line is possible? Well, we can safely assume that there are innumerably many secant lines that are parallel to the tangent line, unless it's a point of inflection, which is not a problem either, because remember what I just told you? I said that only the term in f of x is the derivative. And if you want to have a derivative at a point of inflection where there is no full tangent line, only a half tangent line, you can still have it, but it makes no sense. Right. So this was proved by Euclid over 2,300 years ago. Why can't we use the same approach in mainstream calculus? Very simply this. In mainstream calculus, this expression here does not depend on h. The sum of all the terms in h must be zero because the expression f of x plus h must equal to f of x. In other words, this part here is the slope difference, and it's never zero unless f is a linear function. But in the new calculus, we know that the parallel secant lines have the same slope, but none of the secant lines in the mainstream calculus ever have the same slope. So the statement f prime of x plus h must equal to f prime of x, the slope of the tangent line, is clearly untrue. So that is never equal to the slope of the tangent line unless h is equal to zero, which in the words of Anders Gesor is absolutely not allowed. You can read my Quora debate with him. But doesn't the new calculus method still use limits? No, because those parallel secant lines are fixed and nothing is moving or approaching anything else. It is impossible for a parallel secant line ever to coincide with a tangent line. For if hypothetically it did so, then the secant line would degenerate into a point which cannot have a slope, can it? So there is no pair 0, 0, which can be used in the definition of the parallel line slope. However, because of the ingenious formulation of the new calculus, it's equivalent to setting all terms of m and x equals to zero, even though you don't have to do it, because if you take the auxiliary expression and you add those terms all up, they are zero, okay? It's always zero. The sum of those terms are always zero, as I showed you in here. Look, it doesn't matter where you are. Oops, zero. You see, there's a zero there. And it doesn't matter what function you have, this will work for any smooth function. And you can always know what is the derivative, because the derivative is an expression in x that contains no terms in m and n. And you can say, well, how do you know when to which terms belong to what? Well, if you have an expression which evaluates to zero, you know that that is the slope difference. Otherwise, it wouldn't evaluate to zero. Okay. And another quick way of testing it is you could always just set um, the uh, the terms in m and n to zero, and then see right away that that gives you zero. So for example, 0 minus 0 is 0 plus 0. 0 over anything is 0, isn't it? So I mean, you know, and idiot mainstream mathematics academics, they don't see these things. They just think they know better. So he says, but in practice, okay, and I dealt with that. Is the purpose of this definition just to be more foundationally rigorous? No. The new calculus was 100% rigorous from the moment it was conceived. Well, I shouldn't say conceived. From the moment it was realized in the brain of John Gabriel. Okay. It has been 100% rigorous. There's never been any problem. There's never been any refutation of the new calculus. It is the first rigorous formulation of calculus in human history. Mainstream calculus never has been rigorous, isn't rigorous right now. And actually, I did mainstream calculus a favor by introducing the holy grail of calculus, which explains what Berkeley couldn't explain and what Newton and Leibniz didn't have a clue about. Okay. So it's not a definition to say that a secant line which is parallel to a tangent line has zero slope. It's a very common geometric fact. Hope I've cleared that up. Whoever this person Busy Beaver is, and please do study the links, before you ask questions. I'm not always going to do this, and you're going to think that maybe you're right, but you're not right. You're wrong, okay? Because I don't have time to do this for everybody. If you're not already a subscriber, become one, click like, tell your friends about this, and follow me on academia.edu. I'm John Gabriel. This is New Calculus. Till next time, goodbye.